Hello, welcome to AI in Action. My name is Mari, and I'm here with my husband Jim, and we are about to talk about artificial intelligence. We have a guest today that we're very excited about. Chris, welcome to AI in Action. I would love it if you would take just a second to kind of introduce yourself to our audience, and then Jim has a lot of really interesting questions that I think he wants to ask.
Thank you, Maury. I actually studied history, political science, and philosophy at Rice University, and then went to Columbia Law School, got a law degree, and practiced law for about 5 years. Decided that I really didn't enjoy that, and that I was spending a lot of time in the evenings writing computer games on an old compact portable back in the days when the dinosaurs roamed. Uh, so I decided to go back to school. And I went to Rice University, as it happens again, and studied compilers with Ken Kennedy and Keith Cooper. And then, went out into the world to work on compilers for digital cell phones at TI. And then I got an opportunity to go to Sun Microsystems to be one of the original authors of the hotspot Java virtual machine. And the key thing that myself and two coworkers did was we were the three people who built the first optimizing compiler that was used as a just-in-time compiler, and that made Java performant enough to be really successful. And that was a really cool experience uh, because it gave us an opportunity to really change the way that people did programming. Uh, because Java reduces defects by as much as 70% versus C++, it changed the way that programs were written, and it also changed the way that programs were used and code was used inside systems throughout the world. And so, improved reliability of things like medical systems and banks and so on. And so it really was a very fundamental change in technology that had a big impact. I then went on to do some supercomputer work at Sun. The Oracle purchased Sun, and I did some research work there. But the next really big thing was I joined Qualcomm in 2010 and uh, did some research work with them on heterogeneous computing, basically offloading computations to DSPs to be more power efficient and more performant, which is very relevant in sort of today's AI community, because that's sort of what AI, certainly machine learning programs, really look like today. That's how they're being run. And then joined the product group to work on the design for a microcontroller and build all the tools for that microcontroller that was part of the original 5G modem for Qualcomm. And there again, I got an opportunity to really work on a transformational technology, a technology that's just had a huge impact worldwide in spreading the availability of communications all over the world into areas where the cost model just didn't allow for this type of communication to be available. And now suddenly with 5G, it is
Mm-hmm.
available. So I've been very fortunate. I reached a point where I was just kind of burned out. So I
Yeah.
retired from
I,
Sun.
I don't know why. I mean that's really confusing to
But I
me
don't
as
know
to why
why.
you would all.
Why don't you own it? Why aren't you owning it? Why don't you sitting on a beach somewhere with an umbrella and sipping pina coladas? I mean, you've done your time in the tech space and the burnout. I spent a lot of time in the tech space too. I didn't spend it the way you did, but it is a high burnout place. And
It
as you get
is.
older, it gets
It's
harder
harder.
to do. It gets harder to deal with. I mean, I'm an IT director because I was burned out and wanted to see my kids. So um, it's one of those things where I can certainly understand it. I hate to be the one to break it to you, though. I think they might have messed up Java a bit after you left because Java is really complicated now. I taught a class recently. My son was in. He was doing Java. It's not his favorite language in the world. Um,
Java has gone the same route that C++ has gone, which is just to keep adding more and more
yep.
features and
Feature
getting more
creep.
and more complicated.
Yep.
And in both cases, it's made both languages, much less usable and much less useful. And it's
Oh
a shame.
yeah. When
It's
I
really a
started
shame to see.
I was writing device drivers for companies like Harris Semiconductor, and I used a lot of C++ and C. Actually, I was doing straight C when I started, and then we went to C++. And back then, it really wasn't bad, but I got back into C++ or tried to a few years ago just to kind of see where it was, and it's like, oh no, thank you. This
It's
is
horrible now.
horrible. It's horrible. I'm not even going to touch that.
Okay, should we say that out loud?
Um,
So,
it's
I'll say
probably
it. If Bjorn wants to give me a hard time, he can.
it's probably okay. I mean, if you keep piling in features, eventually anything becomes unusable.
oh,
So
absolutely, absolutely.
so
So I can hear that our phones are ringing there at work. It's
yeah,
amazing what
sorry,
happens when, yeah,
I can't
just
help
just
it there.
ignore them, just ignore them. So let's talk about the next question, Jim.
She's trying to get me
So
off of
yes,
the
otherwise we're
reminiscing
going to be
because
talking about programming languages the whole time.
yeah, I had a friend who was a compiler designer that designed the first Microsoft Fortran compiler. So I I have some background in that too. You mentioned earlier because we were talking about GPU shortages, and I'm even running into some issues with that myself here with some projects I'm doing for the school district. You mentioned earlier something about the DSP work you did and offloading tasks, and this is a conversation I was trying to have with Intel recently too about a better way of doing what they're doing with these. So I'm interested in what you're doing with that in particular. People are talking about it, but what exactly is your venture doing to make this a problem a little less painful for the rest of us?
So right now, most GPU programming for machine learning applications is done with these big libraries where NVIDIA in
CUDA.
particular has this huge set of complex libraries.
Hmm.
Um, and what people are doing to write neural network models is to stitch together these library calls that are pre-baked by NVIDIA. And the problem, one of the many problems with that is that in many cases, the way the library is written isn't suitable for the problem that somebody wants to solve, right? So when you're writing these neural networks, you you need to be able to do things like change the size of the problem set that you're dealing with. So when you have these fixed library calls, they're of a fixed size. They do, exactly one thing. And so in many cases, the developers are going back to NVIDIA and saying, well, we need these 10 extra versions of everything. And NVIDIA says, well, we just don't have enough bandwidth to keep doing that. They've got literally thousands of these things now. And in addition, NVIDIA is struggling now as they put out the next generation of devices. They're struggling to port all these things, right? They have to basically rewrite them for every new GPU generation. And it's a huge cost and a huge overhead. So we want to take a somewhat different approach to it. What we're doing is we're building a compiler that will compile the compute graph from a neural network model down onto a particular device, whether it's an NVIDIA device or an AMD device, and then execute that in a runtime, right? So we build a runtime that actually runs on the GPU, which many people said we couldn't do, but we have done. And the sort of goals here are a couple of things. One is the portability. So now if you write a model, you're not tied to one particular GPU because you've used that GPU's library calls and now you can't do anything else. Instead, you just write your code the way you want the code written and to do the computation that you want to do, and we translate it down onto the hardware. The typical problem with that in the past has been that compilers were not well suited to this problem. And the reason that traditional compilers are not well suited to this problem is because they operate in too low a language paradigm. So if you write a program in C or C++, you're writing a program that's talking about individual or arithmetic statements in a single threaded context. And there's huge technical problems and risks involved in trying to convert that into a wide vector parallel program, which is what GPUs run effectively. And so that's what actually sort of forced people initially into this idea of writing these parallel vector libraries and then calling them. So we're taking a somewhat different approach. Instead of using, the sort of traditional, okay, convert your code into C++ and run it through your C++ compiler, we're taking the code as a raw compute graph, a raw neural network graph representation, and we're optimizing it as the graph. And then we're generating code for that graph itself. So the benefit here is inside our compiler, we're not representing things as individual adds and multiplies and so on. We're representing them as constructs which are inherently concurrent. So we don't have to go do the complex problems of figuring out, is it legal to run these things in parallel? the input that we get tells us when it's legal to run in parallel, and we preserve that information all the way through until we output object code. As a result, the complexity of our system is focused around extracting the best behavior from the hardware, not solving a whole bunch of difficult problems because the language is mismatched to the application.
So this idea you had of almost bypassing the CUDA, the CUDA libraries have made my life easier because when I'm using AI at a top level, I'm using tools like Olama to abstract away the different large language models. But if I decided not to use the CUDA, like I tried to use the Intel, Vino libraries, and they were massive. I mean, I had to download this massive file. I couldn't get it to work right. It was very complex. And the additional problem is that we were at the time we're trying to figure out how to use these different language models on different size GPUs. Are you abstracting away are you going at a lower level? So you're abstracting. I mean, it sounds to me like that you're going to have to port things to all these different GPUs as well to some degree.
So we'll have
So
to
how
port
do you
our
bypass the
system.
porting problem?
And so we port our system in much the same way as the Java virtual machine is ported, right? So what we do is we break down the hardware into a series of parameters that the compiler uses to parameterize the behaviors. So we take information about sizes of memories, about bandwidth of memory connections, about the instruction set and how the instruction set is organized and what it expresses. And then that all gets sort of summarized and embedded into the system. And so when you want to port our system to a new, GPU, for instance, what you need to do is write this hardware description that says, okay, here's what the relevant instructions are that we care about. Here's what the speeds and feeds of the various memories are at the various different hierarchy levels and so on. And all those things allow you to basically tailor the computation to the specific hardware to extract the performance out of it, which is otherwise what human beings do when they write those CUDA libraries, right? The engineers at NVIDIA are doing this by hand. And what we're doing is automating it. And basically what that allows us to do is to generate these high quality kernels, but across a variety of different architectures, not just one specific one.
So is this a similar problem? Because I'm probably misunderstanding the problem because you're at a much deeper level than I am. But is this a kind of similar approach that the guys at DeepSeek had to do when they had this idea of, they were bypassing the CUDA libraries because for a whole different reason, because they're in China. Were they just doing it by hand? Or, I mean, it sounds like yours is, as you said, more automated than hand done. But
So
that was my
what
first
DeepSeek
question.
did by hand is some of the stuff that we're doing in using automation.
Okay.
So DeepSeek did two key things, right? They bypassed the CUDA libraries and they wrote directly in sort of NVIDIA's assembly language. And they did that because they wanted explicit control over memory movement, because that is the biggest performance gap in modern machine learning programs. And so to some extent, the results on DeepSeek validated our approach, because exactly what we're doing is tailoring the computation to basically do explicit control over the memory movement. They did it by rewriting the program for one specific set of parameters and hardware. What we're doing is parameterizing all the behaviors of the memory subsystem. And then we have a runtime which actually manages memory transfers directly. So we have the runtime place data into low-level memory down at the L1 layer, right next to the CPU, to the core ALUs in the GPU. And what that allows us to do is to make sure that we don't have a lot of bottlenecks, that we're not constantly bottlenecked on these memory interconnects. And if you see a lot of these runs today of large-scale inferencing and training, you see that they're getting 10 to 20% utilization on the GPU. It's not that the GPU is not fast or efficient. It's that you can't get the data in and out of the GPU with the current programming models in an effective way. And so these things are terribly underutilized. And
so do you help with a distributed loading kind of problem across multiple GPUs, or do you just make any individual GPU more efficient?
both.
Okay.
So imagine a system like an AMD MI300. It has, a couple of host processors that are x64 based, and then 8 GPUs that are interconnected. So we'll manage that entire node, right? So we'll distribute the computation across all 8 of those GPUs. Then inside the GPUs, they're broken down into a series of 8, what they call XCDs, and each of those control 38 actual GPU processing pipelines. So what you're doing is distributing this thing across a very, very large grid of compute elements. And at each layer, it has different speeds and feeds from memory, different access to the machine resources. And what we're doing is managing all that directly in the runtime. And by doing that, we get better throughput. We utilize the system more efficiently.
So it seems like I understand the problem you're solving and your approach a little better. I'm still curious who exactly your customer is for it. I mean, it sounds like you could sell yourself to Intel because they could certainly use the help,
So,
or AMD.
so
Jim,
it's
Well,
sort
you
of
nice.
to
know,
anybody who wants to lower the cost of running machine language training or machine learning training or machine learning inferencing. So your your chief costs are electricity and hardware, right? So the GPUs are very, very expensive. If you're only utilizing them at 10%, that means that you're not getting a lot of return on that investment. If I can increase that utilization from 10% to 50%, okay, you're getting 5 times as much work done for the same cost. By the way, the electrical utilization on that GPU doesn't vary that much between just it being turned on and it actually running real compute.
Mhm.
It varies
yeah,
some, but it's not as much as you'd like to believe. And so
yeah,
you're
it's
paying
very
for the electricity
spiky
either
too.
way, but you're not
Right.
getting any benefit.
Right. Yeah, the whole, I've got a system here that we're allowing teachers to have access to AI tools, and we run some models locally because for privacy and that kind of thing. They don't tend to be great models to run. I mean, most local models just aren't really that good. They're better for doing pre and post filtering on user queries. But, I've had this thought for a while about if I have all these AI enhanced PCs, why can't I do distributed loading and utilize all these GPUs that are sitting there and doing nothing most of the time? But I haven't really seen anything that allowed me to do that. I mean, most of the time, that's maybe the problem's too hard. Maybe neural nets don't lend themselves to that kind of distributed loading. That's what I was curious about.
So you can do that kind of thing, although that's not really our focus. Um, the difficulty that you're running into is that all the models that run on relatively less powerful compute platforms have limitations in both input sizes and the accuracy of the results.
Mm-hmm.
So what you really want to do is you want to run the even if it's the same model code, if you run it on a more powerful compute platform, what that allows you to do is to hand the model larger sets of weights and biases, i.e., to do better training of the
Mm-hmm.
model.
Mhm.
And once you do that, now the model will produce better results faster. And so you're kind of limited. When you limit your compute resources, you're also limiting the accuracy of the model that you run. And it's not a matter of whether whether you think it's saturating your computer, because none of them saturate the computers right now because they're all memory bound. So, you look at your computer and you say, well, it's not actually working that hard. Well, yeah, the problem is it's totally stalled on data transfers.
Mm-hmm.
Mhm.
And that's the problem that we're trying to solve is say, okay, don't let it be stalled on data transfers. Let it actually spend most of its time running computation. And one effect of that is that a less powerful compute platform can handle a bigger model. That's
Mm.
one of the many effects that you can get out of this. So, but our principal focus really has been, on running models on bigger, beefier hardware because, well, for one thing, there's more money in that, and for another, uh, we're really trying to push the envelope on getting, the accuracy of results and lowering the cost of getting highly accurate results. So the cost model right now is driven by the fact that you have very little utilization for very expensive GPUs. If you can increase the utilization, the effective cost of a given inference, for instance, drops. So example I gave before, if you go from 10% utilization to 50%, now an inference costs 20% of what it used to. Well, there's a lot more people who can pay that 20%.
So do you see like large corporations like Microsoft as your customer in terms of because they build compilers and they build, all these different tools, or do you? I'm not sure what how it would scale or transfer down to the little guys like us, for example, who are the ones that are actually doing the implementations of these AI systems into different applications like here at the school district.
So I think there's a couple of things. One is that, what we're going to provide initially is an inferencing engine. So, if you want to run inferencing, using our inferencing engine will allow you to run it more efficiently. You'll be able to get more inferencing done on whatever hardware it is that you decide to purchase to run. The second thing is that sort of more cloud-based inferencing, which is actually very, very common right now, where people doing queries across, web interfaces into cloud providers. Those guys actually have the hardware, but the hardware is not being utilized well, so they have to charge a lot for it. If you get the
So
utilization rates up, they can charge less, right?
can
And
you
so
can
now
you
suddenly
slide
when
into
you want to access it, it costs you less.
can your tools then slide in place of like if I'm right now we're setting up some cost modeling to try to figure out the best way to get what we're doing across more school districts. School districts always have funding problems, so we're trying to figure out
Yeah,
how to
who
get this
doesn't?
across them. And so everything we've been focused on so far has been locally. The GPUs everything's local, and I mentioned why the privacy, security, all that stuff. But I've also been looking at okay, how do I rent GPUs in the cloud? And they're actually kind of expensive to
Hmm.
rent, and it's really difficult for me to put my arms around the cost modeling. So would you see your tool as something that I could rent GPUs and utilize, or does the people providing the GPUs have to put this in place before I get the benefit?
So the cloud providers are very interested in working with us because, we offer them an opportunity to, you know, offer you a lower cost solution to your problem, right? So that just means they get, more customers, more use, etc. The Microsofts of the world are very interested in what we're doing because they actually spend a lot of money doing AI inferencing internally for their own use, as well as providing services outside. So lowering cost is huge there. Uh, the chip vendors are interested in particular because they really don't. It's very, very expensive for them and very, very difficult for them to compete with NVIDIA. And the reason is that NVIDIA has spent 20 years building up this, huge library of CUDA kernels.
Yeah, I think that's Mari's question number 5 that she put in place. I mean,
Mhm.
and I agree with her. The CUDA libraries are very convenient. I mean, the fact that I can grab a tool that layers, puts an abstraction layer between me and all these different large language models, and the CUDA libraries take care of all that junk underneath. It's very handy. And as I told you earlier, when we tried to use the Intel libraries, I mean, maybe they've gotten better. I haven't tried them, but it was hard, and we
Yeah,
just
and
couldn't make it
there
work.
are various other manufacturers who also have layers to do this that don't work very well either.
Yeah,
So,
AMD is one of those. So I've looked at theirs as well. I mean, think about it. There's not a lot of really big GPU guys in the world, and when you start looking at where I'm going to get mine, you literally make your decision based on whether or not it's got the libraries available for you to be able to easily do this. I
and
do
that's
love
part
the
of what
idea
we're
of the
trying to fix,
compiler thing.
right? That's
Uh,
what we're trying to fix is that if instead of needing these libraries of pre-written kernels, you have a system which can generate high performance code for you on whichever target you're interested in, that changes the economics. It changes the set of choices that you have available to you. Because now, instead of, having only one vendor that you can go to and having to pay however much it costs to get their hardware, now you have a variety of selections of hardware that you can go to at different cost points. And you can still write your models to it conveniently and not have to worry about understanding the details of how that hardware operates or, how it was designed underneath. Right? You write to an abstraction which is literally the uh, neural network graph abstraction, right? So,
yeah.
we're right now, to start, we're simply taking in FX graphs from PyTorch Dynamo. right? Standard way that people tend to write these kinds of neural networks.
Mhm.
And the rest of it is up to us, right? We take in the compute graph and the input tensors and the training information, and we figure out how to run that on the hardware. And in particular, our current work is focused around AMD, but we've got a number of other manufacturers of devices targeted at this market who have expressed a very strong interest in working with us because they're suffering from that problem, right?
Mm-hmm.
They know that their software layers aren't adequate and aren't competitive. They need a better answer, and they can't afford to hire the 20,000 odd engineers that NVIDIA has been using to write and update
So
their CUDA kernels.
Mari and I are doing a presentation in a few days to a bunch of people, and one of the things that we're using as a news article is the fact that Google has got a whole thing where they're giving money to train 30,000 electricians because they need more electricians to wire up power plants because they're using so much power on all these GPUs. Are you saying that you're going to cut down on the number of electricians required because you're going to get 50% utilization instead of 10?
Yep.
So
Hey,
Well,
to me, that's big. That's
so the other
huge.
side of that one was I believe that it was actually Eric Schmidt recently said that he thought that in 10 or 12 years that 97% of the world's power was going to go into doing AI.
Mm.
Well, and I think that's unrealistic, but his point is well taken, which is that AI currently consumes a huge amount of power. If you want to expand it and make it more usable, make it more available, you're looking at more power.
Mm-hmm.
So the flip side of that is that if you can cut the amount of energy that it takes to do an inference by a factor of 5, well, you're really affecting not only the cost but just the availability equation, right? I mean, there's practical limits on how much power you can get delivered right now because of the way the power grids are designed and implemented, right?
yeah, but you remember the old days when you turned on a Pentium and the lights dimmed in the room and there was so much heat
I
coming off
do.
that thing that you could just open the lid up and warm the room up on a cold winter day. And at the time, everybody was saying, at the rate these things are using power, we're gonna shut the planet down. I mean, it was similar kinds of arguments. And along came people like you who went, okay, there's got to be a better way to do this. And of course, Intel, shrunk the transistors. They made things smaller. They did all that other stuff as well, which is required. But I mean, it sounds like you're addressing the other part of that
But the flip
equation.
side of that one is that you get people like Qualcomm, and you got a cell phone right now in your pocket that has the same level of power as a Cray supercomputer did in the early 90s,
Sure.
Mm-hmm.
and it runs
Mm-hmm.
on a battery.
Yeah, the whole
Right.
shrinking thing helps a lot. When you make the transistor smaller, they don't use as much power. So
Right.
it's
But
both
unfortunately,
sides of the
physics is
equation.
fighting you now, right? So they've reached the limit of the shrinks.
They
Things haven't been
have.
getting smaller for quite a while now, and they're giving the appearance of things getting smaller by stacking, right? By making the dies 3-dimensional instead of
Yeah, and that's
two-dimensional.
a geometry problem instead of a physical size problem of the actual transistors.
Right. But the problem is that uh, the amount of energy that they're taking and the amount of heat that they're generating has been not shrinking at the rate of the increase in the number
Yeah.
of transistors, right? So
Right. It's
you're
not
no longer
proportional.
getting the kind of scaling on power utilization that you used to get.
Yeah.
And
Mm-hmm.
Well, Mari
they're
and I used to work in the semiconductor industry, and believe it or not, and part of what we did, we worked with companies that did ion implantation equipment, which was, so we spent a lot of time figuring out how to make things smaller, or at least the companies we
Yep.
worked for did. So we're, as much as she says she's not technology, we are both very
I
much
have
into the technology
I
space.
have
So
been sitting here just thinking about what I'm going to have for
yeah,
dinner
you
and
would.
like thinking
You're
about
such a
the
liar.
next
You
thing I'm
love
going to.
this stuff and you
Yeah,
know it.
no, I seriously, I've really enjoyed listening to Jim have the opportunity to geek out with somebody because,
Somebody old, like somebody as old as I am, because he remembers like Pentiums and that compact you mentioned earlier, and all those other things. So
so, okay,
Perhaps
now
even a good bit older.
I knew that we were going to go over in our time, and it's something that we keep doing all the time, which is fine. Now's when I have to jump in and I have to like ask like one of those last questions, one of those things to
go
kind of
for it.
like okay, AI. We know it's huge. We know it's world changing. I'm so glad that It's making us ask the questions and have the conversations, just like it did whenever they, back in the day when they started talking about energy grids and stuff like that. We're finally having to really dive. I'm sorry, I'm going to say an A word. We're getting to delve into
Hey, I just love
what
that
it's
word.
going to take to make ourselves more efficient when it comes to energy, right? What's all the downsides, Chris? I mean, tell me. Everyone always wants to know. Okay, we've got the utopia. Now, give me the dystopian view of this.
I don't
What's your
think
greatest fear? What's your greatest fear
of AI in general. Is
of
that your question?
AI? Of AI, of where it's going, of where it's headed.
So
Those 50.
any major technological change,
Mm-hmm,
you know, has the sort of the cloud and the silver lining, right? So
mm-hmm,
the silver lining tends to be that when you make a big bump in human productivity in any significant part of the economy, what that does is it brings up the standard of living of everyone.
right,
So that's the really great part. Okay, that's what I see as the silver lining, and that's why I feel strongly about it. That's why I came out of retirement to work on it, is because I think there's a huge upside.
yes,
Okay, there's also always a downside, right? And anytime you do that big a change in the way the economy works and in the equations that drive the economy and drive productivity, you have all kinds of downsides. So, one of the classic ones that we've seen time and time again throughout history is you end up with a lot of people who are sort of displaced, right? Now they have
right,
skills that aren't useful. So if I take the average white collar worker and machine learning makes them, you know, 80% more efficient. Well, that means I'm going to be probably laying off about, 1 in 3, 1 in 4 of those workers because I'm not going to have enough work for them to do.
Or
right.
just not
And now
hiring
they're
as
going to
many.
have to go
Well,
find something else to do
I
to
think
make a
that
living.
something that we need to remember, and it's something that, like, I'm on LinkedIn all the time, and it's one of those things that you read about. It's putting us out of jobs. It's gonna crash our economy. It's gonna take over the world. Skynet, yada yada yada. You name it, it's there. Um, One of the things I really think we need to remember is Jim had a grandfather that was a mechanic. And what happened when they switched from one type
It's
to the other?
generators. My grandfather retired when the automobiles went from generators to basically full DC systems to AC
Alternating. Sure.
to
Right.
alternators. My
My
dad took over at that point, and then when my dad retired, because when they went from the mechanical control systems to computer control systems, I made a computer interface for him to give him a few more years. I basically helped him with the computer interface piece of it because he couldn't figure out how to fix a car because the diagnostics were so different, because
Right.
the computer would try to
right.
compensate for things and all this other stuff, and it was different than the mechanical world. So
Right. And
yes, that is a good
my
example.
father was a postmaster for the US government. And when they switched from hand pitching the mail over to computerized and the
Mechanical
the thing that
sorters, etc.
Yeah.
Yeah.
the automatic sorters and everything, he was like, I'm ready to retire. And so I think that something that people tend to lose sight of is that it is cyclical, and it is something that has happened over and over and
Right.
over. And we have compensated and we have adapted.
But
And,
for thousands of years, this cycle has happened, and it will
right,
happen whether you want it to or not.
right,
But I think it's important to be aware of it, right? It's
exactly.
important to think about, okay, if we're going to make this big of a change, what do we do to help out the people who get displaced? What do we do to deal with the situation of, okay, suddenly now people don't have the right set of skills? In addition, I think there's a big educational side to this, right?
Thank you.
Thank you. I was hoping
You're going
somebody
to
put a plug
go,
in for
Yes.
that. We
you're
needed
going to go
that.
down a different path, right? So
Right.
if you're going to be effective at using these things, a large part of the effectiveness of using machine learning tools is understanding how to ask the right question.
Hmm.
If you ask the right question, you get a good answer. If you ask the wrong question, you get a bad answer.
Hmm.
Teaching people how to ask the right question, teaching people how to think in the right way so that they use the tool effectively is going to become critical, because
Right.
that's going to be the difference between, you know, an 80% improvement in uh, productivity and a 10% improvement in productivity.
Right.
Well,
We keep telling our English teachers and our communication teachers who are so paranoid of what artificial intelligence is currently doing. We're like, look, guys, y'all are more important now than ever because knowing how to ask the questions, knowing how to communicate, knowing how to say things clearly is going to be huge in the world of AI.
Well, and English is a wonderfully expressive language, but it has a problem with precision,
Mm-hmm.
mhm.
and that's partly due to the language, but it's in large part due to the way that people use the language.
Right.
And things people like English teachers are going to be crucial because generating queries for machine learning models requires a great deal of precision in the language that you use,
Mm-hmm.
right? Subtle
Exactly.
differences in your choice of language will give you significant differences in your result just because of the way these things operate. It would take me too long to explain, but I assure you it's absolutely true.
Oh,
And so
I 100% agree. Anyway, we
Mark,
are,
understanding
Jim,
language and utilizing it clearly and effectively is going to become a premium skill.
so
absolutely.
two things, and then
Okay.
because I know we gotta quit.
You're
First of
fine.
all,
You're fine.
I'd like to thank Chris for putting a plug in for education there, because what do we do as AI Ed Pro? We actually go out and teach
Educate.
people,
We
educate them
educate.
on digital literacy and how to use it. The second thing is, thank you for now giving me an answer to that question that I get all the time, which is, don't these things use so much power you're going to kill the planet? Because I do get those questions. And see, now I can say, hey, you know what? There's somebody working on that. They're working on making these things more
More
efficient, better
efficient.
utilize the energy, that kind of stuff. So that was it for
Yes.
me. I know we got to wrap up. So
Absolutely. Chris, thank you so much for coming on today. I really, really appreciate it. We are going to be like, what do we have coming up? We're talking to Llano ISD on Monday evening. We're actually going to be try
bunch
to
of
be
teachers.
prophets in our own village, which is really, really hard to do.
Mhm.
And then we have some more summer development stuff coming on, TCA conferences. We're staying really busy. I have a book, Chris. I have a book that's going to be coming out. It's kind of funny. I put in two titles. One of them was Teachers Are Up to Their Ass in Alligators, Tales from K-12 Classrooms and How AI Might Be Able to Help. And the other one was Teachers Have Bigger Fish to Fry, K-12, AI Might Be Able to Help. I had to go with Teachers Have Bigger Fish to Fry because one of the teachers was like, I can't put Teachers Are Up to Their Asses and Alligators on a bookcase behind my kids in the third grade. So I
Can't put
ended up
ass
having to
on.
go with the more politically correct. I know, and
You might have gone with eyes, but I think probably the other one still is better.
yeah, well, I put the capital A with the little,
Oh yeah, no, I
I didn't
understand the
spell the
reasoning.
word out, but so
Yeah. All right.
okay, so we are going to go now. I hope that you guys have a marvelous rest of the week.
Thank you,
Thank you,
Chris.
Chris, for being
Appreciate
here.
it.
Thank you. Enjoyed it.